The harmonic series is a series 1 over n. And this series of 1 over n, if you analyze the sequence by itself is just this part here. Here we can see that for the sequence, if you put in bigger and bigger numbers, you would have 1 over 1, 1 over 2, 1 over 3, and so on. And we're going to prove that if you add together all these numbers, the sum is going to be plus infinity. So the series is going to diverge to plus infinity. So the first number we plug in is 1 just because we can't insert 0 since we can't divide by 0, and we insert all the numbers up to plus infinity. So in order to prove this, we're going to use the partial sum, and the partial sum, so for example, if you want to find S1 would be the first term, which would just be 1 over 1. S2 would be the sum of the first two terms, so A1 plus A2, and so on. So generally we can say that the difference between any two partial sums that are right after each other is going to be the term that you're adding. So for example here, we could say that S3 equals S2 plus A3. So you always take what you had before, and then you just add the new term. So generally we can say that any partial sum is the previous partial sum, so Sn minus 1, plus the new term An. So since we can see that An is always going to be positive because we can only insert natural numbers, which are 1, 2, 3, 4, and so on, if An is positive, we can be sure that we're always adding positive values, and so the sum must be increasing. And if something is increasing, it can do one of two things. It can either converge or it can diverge to plus infinity. But it definitely cannot be irregular, and it also cannot diverge to minus infinity. So we're going to prove specifically that it diverges. And in order to diverge, it has to be unbounded. Well, in order to be convergent, it would have to be bounded. So we just have to prove that it's unbounded. And that's going to be enough to be able to conclude that it's not convergent, and so it must be divergent to plus infinity. So if we start writing out a few of the partial sums, we have S1, as we said, was just A1. So that would be 1 over 1. So 1. If we do S2, that would be the first two terms added together, A1 plus A2. So that would be 1 plus 1 over 2. Then if we skip ahead a bit, we're just going to go to S4. We're going to take A1 plus A2 plus A3 plus A4, which would be 1 plus a half plus a third plus a fourth. So if we start approximating this, we can say that 1/3 is definitely more than a fourth since the denominator is smaller. So all of this whole sum, is going to be bigger than 1 plus a half plus a fourth plus a fourth. This is just to get an approximation of the sum. And if you put this together, this would be 1/2. So we have 1 plus a half plus a half. And rather than writing that as just 2, we're going to write that as 1 plus 2 times a half. This is just to see the pattern with the next partial sums. So far we can say that S4 is bigger than all of this. If we keep on going, we're going to skip ahead to S8. So S8 would be all the sums added together up to A8. So that would be 1 plus a half plus a third plus a fourth plus a fifth all the way up to 1/8. And so again, if we approximate, we can say that this part here, the 1/3, just like before, 1/3 is definitely greater than 1/4. So if we just write that as 1/4 plus 1/4, we would be underestimating our sum. Then we can do the same thing for the ones from between 1/5 and 1/7. So each of these are individually greater than 1/8. So if each of them is greater than 1/8, then again we can be sure that this sum that we have on the left is greater than this plus an eighth plus an eighth plus an eighth plus an eighth. And so we can see that this was 1/2 just like before, and this here is also 1/2, which means that overall we have 1 plus a half plus a half plus a half, which will be 1 plus 3 times a half. So S8 is going to be greater than that. So the idea is that if you take all the powers of 2 for the number here for your partial sum, S4 was the same as S of 2 squared, while S8 was the same as S of 2 cubed. So now we can generalize and say that if we kept on going and we took S of any power of 2, so generally 2k, the number that you have over here for the power always corresponds to the number of 1/2. So generally we can say that S of 2k is going to be greater than 1 plus k times a half. So the idea is that no matter what k you pick, if you then calculate this, your sum is always going to be greater than that. So what this tells us is that the partial sum is definitely unbounded above. Because for every k we pick, we will always have the partial sum, which is greater than that. And since we said at the beginning that the options for the partial sum were to converge or diverge to plus infinity, if we know that it's unbounded, then the only thing that it can actually do in the end is diverge to plus infinity. So since S sign is divergent to plus infinity, and a series is just a limit of the partial sum, then also the series of an, which is the limit of Sn, in this case from 1 to infinity, this is also going to be divergent to plus infinity. So just so you know, for the generalized harmonic series, there's also another part, which is when the power in the denominator is a power greater than 1. But that one is not in the syllabus to prove because you would need integrals which aren't in the syllabus at all.